Dear students, let's talk about steel structures in this video. We can start with the structure and floor concept, and then we can look for how we can produce steel components like posts or beams or bracings, how we can connect them, and how we can do the steel floor systems. Also, we need to examine the protection methods against fire and corrosion. Let's remember what we have learned about the structure first. As you remember, this is our classification of building products. However, it can help us with the design process as well. In the first step, this is what we do. We make decisions about the building mass, like its geometrical shape, visual aspects, colors, transparency, and location, and relationship with the environmental factors. This group of decisions, they will be used in order to make more detailed decisions about the units. Units will be the living areas for our user, and these can be closed, semi-closed, or open areas. In that step, we are going to make decisions about the building unit properties, like the sizes, the height, their locations, and how they are going to be connected to each other, and what kind of living areas they are going to provide for the user. As you can remember easily, each one of them will be specified for a certain function, or it can change, of course, according to our design. And all these functions, like preparing the food or sleeping, relaxing, in order to execute these functions and protection of the user, obviously, we need building elements. These are the integral products, and we can create them by either combining the materials pieces or components, and each one of these elements will physically meet one or some of the functions of a building, like the roof, the walls, the floor, and structure. And we can design these elements according to the functions and the previous decisions, the visual decisions. And as we create these elements, each one will create loads because of their weight. And according to the location and other environmental factors, additional to vertical loads, there can be lateral loads like earthquake or wind. So we need the structure. That's the element, a building structure, in order to keep the form intact, the form of the building intact. And that element will work to meet all the loads. Vertical, horizontal, it doesn't matter. All the loads related to the building, the structure will carry them and transfer them safely to the ground. Structure will include components like columns, vertical components, or beams, horizontal components. And these components need to be integrated with one of other our building elements. That's the floors. A floor can be used to provide living areas for the user. It's where the load transfer starts. It will create a boundary for our spaces. And if there are two neighboring spaces, then it can work for separation, insulation between these neighboring spaces. And like the structure, floor element will have its own components. There can be one or more components according to our design, our decisions. And that middle part, it's called the floor structure. Uh, as you can see, we have the same word, but with different meanings. This is the building structure. It's an element, and it has its own components. And that's another element, floor, and one of its components is the floor structure. A building structure will work to keep the building's form, geometrical shape intact. It will prevent it collapsing down, losing its shape. And it's the same with the floor structure. This time, that component will work to hold the geometrical shape of the floor and prevent it from collapsing down. And it will work only to carry the loads that are applied directly on this floor. However, building structure will carry all the loads related to the building. And floor structure is the first component that the load transfer begins because when we step on a room, when we enter a room, when we are on the floor, that's how it works. Our weights, the weights of the furniture, we create all these vertical loads, and floor structure is the first component to meet and carry them, and it needs to be integrated with beams and columns, because floor structure will transfer its loads to the beams, and the beams will transfer their loads to the columns. And it will go like that. In the last videos, we learned how to create this floor structure and beams and columns out of reinforced concrete. In order to do that, we need materials, concrete and steel. But again, as you remember, these doesn't have any geometrical shapes. So by using these steel materials, first we need to create these bars. Uh, these are steel reinforcement bars, and we need to combine them with the concrete to create reinforced concrete beams, columns, and floor structure. Now, let's talk about how we can do all these components out of steel. But this time we need different shapes like this I-shaped profile or L-shaped or T-shaped. That can be a box profile or a pipe profile. We have different options. And when we connect them to each other, these will be our columns or studs, the vertical components. They will be connected to each other with beams, and with additional girders, we can create the floors. Uh, what is steel and how we can produce necessary components? We don't have steel in nature, obviously. First, we start with the iron. Iron is one of the metals, and like the others, metals are often extracted from earth by means of mining ores. Uh, we start with the ore. It looks like a stone, but it's not. Ores are generally minerals. These are the oxidized forms of metals. Uh, like magnetic. As you can see here, we have iron atoms, but they are not free. They are combined with oxygen of the air. So this is the oxidized form. This is one other example that we can provide iron, hematite. Again, it has the same type of atoms, but with different quantity and different types of connection, obviously. We need to heat the ore in a factory by using very large kilns, but there needs to be a reducing agent because we don't want that oxygen. So we can heat these ores with materials that have carbon in them, and with the heat, the carbon will be combined with the oxygen in the air. We will have this carbon monoxide, and again, with the help of the heat, there will be a near chemical reaction between hematite and carbon monoxide. We will have carbon dioxide and free uh, iron atoms. That's what we want to achieve. And it's generally because of the high heat, it's generally in this melted form. And at that point, we need to create these definite geometrical shapes uh, to turn that material into pieces like that one or this one. But how are we going to do that? How are we create these definite solid shapes out of this melted iron? There are different options, but these are the most common ones. We can either cast them. Casting means creating holes in some sort of molds, and when we pour the melted iron into these voids and let it cool, solidify, the end product will have this shape of this void, or we can force them through a gap in the desired shape. Uh, like this example, the melted half liquid substance is forced through these heavy cylinders, and from one end and from the other end, we get these thin sheets. That's called hot rolling. Uh, this is called an eye profile because its section has this eye letter shape, or we can call it H profile or double T. There are different namings. They are all the same thing. And this part, this upper part and lower part, these are called flanges. And the middle part, it's called the web. Uh, and there are two main shapes here, and there's a distinct difference. They all look like letter I. However, this flange parts of the first one is wider, larger. The second one has narrower flanges. That's why we call the first one V profile or W profile, W of the wide flange. And that's I profile, or we can say S profile as the standard profile or normal profile. But instead of this I or W profile shaped, we can create L-shaped, or C-shaped, or Z-shaped, T-shaped, or we don't need that already made profiles. We can custom our own profiles out of these sheets. These are thin metal sheets, iron or steel sheets. And by using these sheets, by combining them in various forms, we can create our own custom shapes. The other group will be the pipe profile or box profile, and these are called HSS shaped. It's the hollow structural section as it has this void in the middle part. We get hematite or magnetit, and we create these different shapes. These are pieces, and we can use them as the components of this structural system. Like we can have columns out of these profiles. These can be called posts as well. They are the same thing. Column and post, they are the same thing, but with a structural system made out of steel or timber, we prefer post instead of columns. We can create beams, main beams, or girders. As you can remember, main beams are the ones that connect two columns to each other. Girders are the supporter, smaller beams. They don't connect the columns. They connect two main beams in order to create the floor. Or help with the floor, their all combination will create a steel frame. That's what we call it. And there are different companies, firms that produce these profiles, and when you search on the internet, there can be some catalogs of these companies, and they give us the information about the sizes and the other properties, like this one here. This is a W-shaped profile, and this is B centimeters or millimeters, and that's H for the height, and this is the thickness. As you can see, there are different options. The first one has this 96 millimeters for the H and 100 millimeters for the B. If I want, I can have a bigger one or even a much bigger one. And obviously, the as the profile gets bigger and thicker, its load-bearing capacity will increase accordingly. What kind of properties we need to provide for these components, for the posts, beams, and girders? Uh, for the steel posts, we can have any shape like this W shape, but if we change the shape or the sizes, uh, get a bigger one, obviously it will affect its load-bearing capacity or resistance against deformation. And these needs to be calculated by a civil engineer. That's very important. In order to make the final decision, to do an accurate decision, a civil engineer needs to do the calculations based on our design. He needs to or she needs to indicate the possible loads and do the calculation and pick an accurate size and shape. For the beams, again, we can use this I-shaped profile, Like if the height of the profile is between 80 to 600 millimeters, and the width of the profile is between 42 to 215 millimeters. The span, the length of the uh, beam can be in between 40 to 9 meters. We can have this span with this size. With the W-shaped profile, if the height is in between 100 and 240 millimeters and the width is between the same numbers, then as you can see here, we can go up to 15 meters. The span can be enlarged. Uh, Here is a rule of thumb that you can use in your project for the height of the main beam. If I want to make a decision for the proper height, necessary height of a main beam, then I can just divide the span by 20. That's the span that I want to create according to my unit decisions. I need that void, that volume. That means that I can have a column here, but I don't want any columns in this direction up to that point, and that will create the span so that I will have a big unit underneath. So I have this with the size, this measurement, I can just divide it by 20. And the height of the girder, I can divide the span by 15. uh, as you remember, girders are the smaller beams to support the floor. This is a different span. I can divide it by 15 in order to find the proper height for a girder. And the width of the profile, that width of the profile, it needs to be proportional with the height of the profile. It can either be half of the height or one third of the height, or if you are dealing with W-shaped profiles, it can be equal to the height of the profile. What if we want to increase the span? What if we need bigger spans, bigger volumes? That means that we need to change the shape. But as the profile gets bigger, it will get heavier. And we don't want that in our structure. So instead of a ready shaped profile, we can create our own profiles out of these sheets. Like I can get a long sheet, a thick sheet, and I can have these L-shaped little profiles and connect them with horizontal bigger sheets, something like this. As you can see, I have a very large beam, but it's lighter than the ready profile. So I can use them to create larger structures, bigger spans. There are some other ways to make lighter beams. So instead of this very heavy and very big beam, I can have this one and cut it in this trapezoidal shape into two half pieces and reconnect it uh, by welding at these points like that. So I will have a bigger height. I can have a bigger span, but with the same weight without increasing the weight. These are called castellated beams, or in Turkish we call kastel kirişi or petek kiriş for that. And there are other options to create even bigger ones, like this one here. I can have this L-shaped profile, four of them. I can connect them with a bent bar like this. This is the upper chord and this is the lower chord. These two L-shaped profiles will create the upper one and two more for the lower one. And I will have a band bar, a bar, steel bar, and I can bend it in this zigzag form and connect these chords together. And that is called an open web joist or trust web. This is düzlem kafes in Turkish. Düzlem kafes kiriş. That's called a kafes. And it's in one direction. So it's düzlem, open web joist or trusted joist. Or if I need a larger one, then instead of a bent bar, I can have an I profile for the upper chord, a bigger one, a T profile for the lower chord, and connect them with these L-shaped profiles like that. The same logic, a bigger one. And this first group, it's called K series. And the second one, it's called LH or DLH series. Here are the two examples. As you can see, this is created with a band bar, and this is created with the L-shaped profiles, the bigger one. And again, you can use that in your school projects. A 200 millimeter height K series, the height of the beam, if it is 200 millimeter, then we can span up to that distance between two columns can be up to 4 to 5 meters. A 762 millimeters height key series, it can span up to 18 meters. This 610 millimeter height LH series, it can span up to 11 to 14 meters. And if I increase the height of the DLH series up to 1,830 millimeters, then I can have a span up to 44 meters. These are from Chink's book. So you can use these in your school projects. However, in real life, please don't forget, a civil engineer needs to calculate all these things. Here are some examples. These are open web joists in different shapes. As you can see here, there is a column there, another one here, and this open web joist can span in between these columns, so I can have a large volume underneath. Uh, how can we provide structural stability? Uh, we need bracings and we need to be careful about the connections. Uh, Lateral loads, they can affect the structure horizontally and like the wind or the earthquake loads. And the frame of columns and beams, they can deform because of the lateral loads like this. So this is something that we don't want. It's different from the reinforced concrete connections. Since we have larger columns and beams for reinforced concrete and they are more stable, it's harder to deform the structure like that with lateral loads. But since steel is very fragile compared to reinforced concrete, it can easily deform under lateral loads. So for the structural stability, that's what we can do. We can have bracings. These are diagonally shaped profiles, uh, and we can connect them here from this connection between column and beam to the other connection or the other column and beam. And so the structure, the whole structure will be more stable. And how can we do the connections? This is my column and that will be my beam. So I can either have smaller L-shaped profiles in the two sides of this beam and create holes on the flange of this column and web of this beam, so that with these L-shaped profiles, I can have bolts. That's what we call a bolted connection. As you can see, these are like large screws, and there is this, that's the bolt. In Turkish, we call it bulon, and there is a nut, somun. So we can just screw it like that, so they will be connected to each other, or other option. This creates a more flexible connection depending on the sizes of the hole and the bolt and the other properties. Or instead of bolted connection, we can have welded connection, kaynaklama in Turkish. As you can see that there's a black line. It looks like it's burned, and indeed it is burned. This is a welding mask, and the builder, it holds a source of heat. It's a very high level of heat. It produces a very high level of heat. And uh, here, uh, uh, it's kind of a chemical reaction. It creates a kind of a chemical reaction. There is two pieces of metal, a separate metal pieces. These are, and I want to connect them together. So I use a third metal, and with this high level of heat, I let it melt and freeze in this gap like a glue. It's a non-flexible connection. It creates a non-flexible connection. And each one of these points, as you can see, there are points all through this line. Each one of these points, it's a connection. And these are called points, punto in Turkish. Again, the number of these points, it needs to be calculated by a structural engineer. Uh, Same thing with the bolts. Again, how many bolts? What will be the size of the bolt? What will be the size of the hole for the bolt? Again, these needs to be calculated because they will affect the load bearing capacity. If I have a post like that and there is a reinforced concrete thing here, then I can use the same techniques, either bolted connection or welded connection, like that, in order to have my post in that upright position. So I can have this sheet. It's a thick sheet, as you can see. I can bolt it on the surface of the reinforced concrete, and I can weld my beam like this with these side supports. Do the same thing with the circular pipe posts. How can we create these floors? Now I have the structure, the building structure with its components, beams and posts, and I want to create horizontal surfaces here, and in order to create a horizontal stable surface here, I can use some sort of boards. These can be made out of timber, they can be made out of concrete, a light concrete, and these are very thin boards. Uh, as you can see, the width and the length is much bigger compared to its thickness. So I can have lots of these boards. I want to place them like that, but there's no support here. They will just fall down. I need to divide this whole area, this whole void, into smaller gaps. There I can use the girders, the smaller beams. These are the same profiles. These can be the same profiles like W profile, or I can use T profiles or L profiles. It doesn't matter. But there are the smaller versions of bigger beams, main beams. Uh, like that, I can connect two webs of the main beams to each other with these smaller girders. Now I can place my boards easily and they won't fall down. These girders will support that board. And with those boards, I can have my floor. That's what we call a metal decking. And if I want, I can use steel sheets for these boards. These are very thin sheets, and they are, as you can see, folded in this trapezoidal shape. Because it's steel sheet with its plain surface, it won't hold. It will just bend down. But if I just fold it in this trapezoidal sheet like that, then it will hold. It will be more stable. That's what we call trapez levha in Turkish. I can have that, and I can bolt it over these girders, and I will have my surface there. Instead of this trapezoidal shape, I can just have this wave shape. That's what we call corrugated steel sheets, ondule. So these trapeze ondulate, it's the name of the geometrical shape. As you can see, I can bolt them easily, and over that steel sheet, I can pour concrete. It's not a very thick concrete. This height can only be 5 millimeters. It'll be 5 centimeters, sorry. It'll be enough. And it's just concrete. It's not reinforced concrete, but we can have string-like very thin wires to prevent the cracks. These are for the anti-crack measure for the concrete, and that's how we create our steel floors. But we need to protect these components against fire and corrosion, especially. Uh, Fire and corrosion, they are almost nearly not the corrosion, but rusting. Uh, Nearly same reaction. Corrosion here, corrosion in Turkish, it's not the same thing with rusting. In some metals, we first have rusting, and due to that rusting, we have corrosion. It's a kind of chemical abrasion. The rusting and fire, they are both caused by a chemical reaction called redox. It's the short form for reduction oxidation reaction. And it's the transfer of electrons between two substances. Like this one here, there are two different atoms. And if they transfer electrons from one to the other one, that's what we call a redox reaction. Uh, One of them loses electrons, and that's the oxidized one. That's what we call it's oxidized, and in Turkish yükseltgenme. And the other one gains an electron. That's the reduced one, indirgenme. It can occur between different subjects and the oxygen atoms in the air. Like this apple, when you cut an apple in half without its protective skin, and if you wait a little bit, then you will see that the surface of the apple will get brownish. That's the same reaction. The electrons of the enzyme are transferred to the oxygen in the air. Apple is oxidized. It loses electrons. Oxygen is reduced, it gains electrons, and it can occur very slowly or very quickly. The quick version is the obviously fire. The slow version is rusting due to corrosion in metals like iron and steel, and it can take years. And in case of fire, we need to protect the structure. It doesn't matter if it's made out of concrete or steel or timber. We know that timber is a substance that can burn easily, and iron profiles or reinforced concrete components, these are objects that they don't get burned. However, they are susceptible to fire damage. As you can see, it burns. And due to the high temperatures, in case of a fire, these profiles they start to melt and they are deformed, and there's a risk of collapsing down. And concrete it explodes in case of high temperatures. Uh, and the best one against fire damage is the timber here, because as the outer surface of the timber components, as they get burned, this thickness of charcoal layer, it prevents it from burning, keep burning. So it works like a heat insulation. It stops the heat reaching into the inner layers of the component. So the structure will not collapse down. It will provide us more time to evacuate the users. As you can see here, this is a timber beam. It is burned, but it is still there. It didn't collapse down. However, the iron profiles, steel profiles, they melted and caused the structure to collapse down. We need, if we want to protect the components against fire, we need heat insulation. And there is this heat transfer. We need to stop it. As you know, with things without any voids inside, the heat is transferred very quickly, like this metal spoon. Since there are no gaps in between its molecules, it transfers the heat very quickly. So there is no butter; it's already melted. What with wooden, objects, since there are lots of gaps, air gaps in between its molecules, the heat transfer slows down, so there's still butter. It hasn't melted down. That's why we prefer wearing thick wool sweaters or jumpers during the winter time. Uh, there are lots of air gaps in between these fibers, and it helps to keep the heat inside. We don't lose heat very quickly. If you want to protect our steel components against fire damage, then we can use paints. There are some special paints. These are some chemical substances, obviously, and in case of the fire, they change shape. We can have plasters, we can have glass wool or rock wool sheets, or we can use gypsum. The paints, these are called intumescent paints. When you apply them, you can spray them on all sides of the profile. You can just cover the whole surface of the profile with this spray paint. And in case of the increased temperatures, this paint starts to change its shape. It enlarges, it expands, and that expansion will create a heat barrier and protect the steel component. We can have plasters. It's the mixture, obviously, and there's polystyrene and gypsum mixed into this paste. We can use that paste to cover the surface of the profile. It will again help with the protection of uh, heat transfer heat transfer. We can have glass wool, rock wool, cam yünü, taş yünü, and these are indeed made out of either volcanic rocks or glass. There is this big machine which creates these very fine fibers out of these rocks, and we gather them and compress them into these sheets or boards. And these brownish ones are generally rock wool, and more yellowish ones, these are the glass wool. And if we cover the whole surfaces of the profile, these, since they are made out of rock or glass, they don't get burned and they provide a high level of heat insulation. And gypsum is a very good material. Again, it doesn't get burned and it provides a very high level of heat insulation. Like this side of the gypsum board, there is this fire, and in the other side, there is our profile. Uh, Approximately, if this side hits the 1000 centigrade Celsius, the inner part is much cooler, and the other part is again much cooler because it doesn't let heat to be transferred through its section. The corrosion, it's the same logic. This is rusting in metals like iron and steel. First, we get rusting. It's the oxidation reaction. It's the formation of rusts as the atoms of the iron and the atoms of the oxygen react with the help of humidity. Uh, there is this other substance, chemical substance created as the end product of that reaction, and that's what causes the corrosion. It's the abrasion of the metal. These leaves are just melt away and disappear in time, and no, there is no profile left. And again, if we want to prevent corrosion, then we need to stop that electron transfer between the metal atoms and oxygen atoms in the air. We need to prevent it, disconnect it. And there is a way that we call galvanization. And it's the steel profiles are dipped into melted zinc so that they are all covered with zinc. Zinc is a substance, a metal that doesn't get rusted, and this is what we get. It's the galvanized steel, so it's protected. Or here is the actual photo of that. It's a melted zinc bath. Or we can have painting. And obviously, this is a different type of painting, a different chemical substance. It's a coat of red lead aluminum paint, and If we cover cover the whole surface of the metal, then the connection of the oxygen atoms will stop, obviously. But we cannot damage. We cannot cut. We cannot create holes, or we cannot scratch the surface. Otherwise, this coating of melted zinc or aluminum paint will wear away, and the oxidation can start again. And in that case, we need to create the whole profile, do everything that we need to do, and then as a last step, we can do the galvanization or painting. And we need to protect it from scratching, or we can prefer stainless steel instead. It has chromium atoms in it, and when chromium meets with the oxygen in the air, instantly this layer of chromium oxide is mm, created, and it's a protective layer. It inherently disconnects the relationship of oxygen and the steel atoms here. And it doesn't matter if we cut the substance instantly. At that moment, again, a new layer will be formed, and it will continue to protect the steel. So these are all the topics that I wanted to share about steel structures. Hopefully, in our next video, we can talk about timber structures. Thank you for listening. See you.